which is going to be a lot of the time, right? Because if it were super, super easy to do, it's probably a problem that's already been solved and you're not working on it. And if it's completely impossible, that's also probably not a problem you're working on. So a lot of the time you're going to be in this regime where you've got something that's a little tricky about trying to fit a model to your data. So I'll start off as I have every day and remind you that this is all about making modeling choices, right? There's a lot of decisions that we make whenever we're building a model to try to describe whatever processes are going on. We've talked about the physical modeling yesterday in the context of hierarchical modeling. We talked about samplers on Wednesday. So that's the machinery that you use to actually draw samples from the posterior. And today we're going to be talking about model specification. So these are pretty much all things you do that don't actually change anything mathematically about what's going on with your model. It's all of these tricks you can use to warp things in order to make the math more tractable, but at the end of the day, things end up being totally equivalent. All right, and so let's start with our good friend, the linear model. So this is the obvious way that you could parameterize this model. But if we wanted to specify this model differently in order to improve it, and by that I don't mean like adding in different variables or choosing a quadratic instead of a linear. I mean, let's keep this mathematically equivalent. We're still just fitting a line. How could we change this to actually improve how the sampler might behave and how robust of a fit we're going to get? Any ideas? Yeah.
You can maybe include something to do with like the air. I'm not really sure if but
yes, you could. That's a good thing to think about. That wasn't the question I was asking. But yeah, I mean, you've already seen from this problem that these are not Gaussian distributed data. So you would in practice actually want to include that. But I'm talking about how could you change this y equals mx plus b, just literally how you've like parameterized the model and written down the equation. You guys think of anything you could do that might make this a little bit easier to sample from?
You've shared the slides on Zoom.
Oh, yes. Apologies to everyone on Zoom. They should be able to see that now. All right. Cool. Yeah.
Could you normalize, like, just so you're not like sampling from 10 to -10, but 1 to -1?
Yeah, exactly. And you can do that on both the X and the Y direction, right? For this specific data set, it's really not going to matter, both because it's just a simple line and because the range and domain of the problem are both approximately the same. They're both 10. But you can imagine you have a problem where your x-axis spans values from 0 to 1, and your y-axis spans values of many orders of magnitude, and for whatever reason you haven't condensed it down to a log scale. Most modern samplers are going to do a good job with automatically inferring that you've got very different scales on the different axes. But especially if you get into high parameter space, just pre-normalizing the data, just shifting everything to just a standard range of 0 to 1 or -1 to 1 can make your sampler behave much better and everything go a lot faster. The bottom line is that the more you're relying on your sampler to do your thinking for you, the more work it's going to have to do and the slower it's going to be. So again, for this specific problem, it doesn't matter, but a lot of the times you can improve how the sampler behaves by normalizing the data. There is one other thing that I can think of that you might want to do, and that would be centering the data, right? So we're fitting a line, and if you notice, by parameterizing it like this, mx plus b, we're placing the intercept right here. And that implicitly gives more weight to the points out here. You can think of it in terms of having a longer lever arm, right? You're further away from the pivot point. And so small changes in the uncertainty or the positions of these points is going to have a much greater impact on the results than the points over here. So you can either, renormalize and recenter the data, or you can reformulate your model such that your intercept point is in the middle of the data. And then it's more like a seesaw rather than a hinge. And again, in this specific problem, it's well constrained by the data. It's not going to matter. But in other cases, it can really, really make a difference. Any questions on those two things? All right, so let's do one more practice problem with parameterization. So a sinusoid model. How could we reparameterize this in order to get a better fit? Any thoughts? Yeah. So you're saying shift everything so that the phi is at 0? That would work if we have some reason ahead of time to know what the phi is. But if the phi is one of our fitting parameters, then that's not going to do as much. Yeah. Anything else? Yeah.
Like a phase fold?
You could, yeah. If you have some prior knowledge that phase fold, but that would presume you already know what the period is. Yeah. Yeah.
We hypothesize in polar coordinates. So
Sure. Tell me what you mean there.
I mean, what you could do is then you change your axes instead of just worrying about the x and y. We could worry about the theta specification more so than x and y.
Yeah.
So,
Yeah, you can certainly do that. Yep. I think that's equivalent to what I had in mind, which is instead of having the phase in here, you split it up into A sine the argument plus B cosine the argument. Yeah. And what that does is that takes one of the variables outside of the sine function, right? The closer you can be to a linearized function, generally the easier things are going to be to fit. So whenever you've got, a variable in an exponent or a variable inside of a trigonometric function or inside of a logarithm, it's just a more complicated conditional relationship between the variables. And so your sampler is going to have to navigate this more curving topology, and it's going to be harder to do. So that simple step of breaking this into polar coordinates, right, A sine plus B cosine, it's more nearly orthogonal. It's going to be a lot easier to sample from. The other thing I would do with this problem is reparameterize in terms of frequency rather than in terms of period. Right? And you could place, say, log uniform priors on period. But if you put linear priors on your period, you are implicitly giving more weight to the longer periods. Because if you think about it, right, in every decade, there's going to be more weight, right? There's as much weight here as there is here. And so if we care about trying to sample the very short periods, we're not going to be able to do that. So one way to fix that is to put a log uniform rather than a uniform prior on period. The other way is just to reparameterize in terms of frequency and then put a linear prior on frequency. The nice thing about working in frequency space, it works for period too, but there's very natural bounds that you can put on it. Right? You can define the longest period, the lowest frequency based on the baseline, and then vice versa with the Nyquist frequency. So again, with this specific problem, it's probably not really going to matter. You've got a lot of data, the uncertainties are small, but look at the context of whatever problem you're looking at, see if there's some way to reparameterize in order to get it to something that is more nearly orthogonal. Right? I say nearly orthogonal on purpose because you're not always going to be able to get things perfectly orthogonal. And even if you are, it's often just not worth the headache to try to perfectly linearize or perfectly get it orthogonal. Your samplers can handle some pretty strong covariances. You're not trying to make it perfectly easy. You don't need to get everything to be a Gaussian. But the closer you can get to that, again, the easier time your sampler is going to have, the faster it will go. So don't outsource your thinking to the sampler. All right. And just one thing to be very careful of, anytime you do a change of variables, right, you need to account for the change of variable formula, right? So you need to calculate the Jacobian. That's the same thing as, everyone saw in undergrad when you go from rectangular to polar or spherical or cylindrical coordinates, that extra term that ends up inside the integral. You'll need to calculate that for whatever your coordinate transformation is that you're doing to warp the data. That's equivalent to me saying that a log uniform prior on period is the same as a linear prior on frequency. So you can deal with that by adjusting what your priors are, or by multiplying another factor into your equation. I belabor this point because this is something that I encountered in my own research. The Kepler team did years and years of work analyzing the data, and half a decade after the fact, we realized that they had forgotten to account for this and had introduced an implicit prior on some of the data, which had skewed some of the results. So it's a very sneaky problem that's easy to miss. Okay, so any questions on reparametrizing before we move on to the next trick? Okay, so reparametrizing, that's one way you can change the shape of the posterior topology. Another way that you can do it is with this technique called importance sampling. And to be crystal clear, importance sampling is not a new sampler. Right? The terminology is the same when we say sampling, but this is a way to approach a sampling problem. It's not a sampler like a nested sampler, an MCMC sampler, or parallel tempering sampler. So when you read about importance sampling, it's often presented in this way that says, oh, if you've got a difficult to sample from distribution, just sample from some other related distribution and then recast it to your original distribution. I've always found that explanation really confusing. It's never clicked for me. I'm saying it because at some point you'll probably see it in the literature, and if you find it confusing, at least now you'll know that it's talking about the same thing. In a Bayesian sense, I like to think about importance sampling in terms of priors. Right? So up until now, we've exclusively talked about priors in terms of actually putting your prior knowledge onto the problem. And you're trying to figure out what your prior really should be. And this is maybe how you've always seen priors presented. But another thing that you can use priors to do is to kind of herd your sampler into the area that you want it to be in. And in this context, you can think of it like adding a bias or adding a potential to the problem. So illustrating it here, right? See, we've got this distribution we're trying to sample from, which has a very long tail, which is maybe difficult to get samples from. If you were just to run your sampler directly on this, you would quickly get lots of samples in this region and very few in this region over here. Now, as always, if you ran your sampler for an infinite amount of time, you would eventually build up samples here, but you'd be wasting a lot of time because you'd end up with 1 million times more samples than you need over here than you need over here. So what we want to do is we want to guide the sampler to spend a little bit more time in the tails of the distribution so that our relative sampling efficiency across all regions of the posterior space is more equal. And so we end up with roughly comparable resolution in the different regions. And so we do that by adding this prior bias, this psi function, to the samples. And you can literally add this into your model the same way you would add any other prior. Conceptually, it's not your prior belief that the model actually should be more over here. In fact, it's kind of the opposite. It's your prior belief that your model's not over here, but you want to spend time over here. Yeah.
Is this what Matplotlib does when you do the color power cycle scaling? So when you change your scaling for color in a
Mhm.
plot from linear to like square root scaling or logarithmic scaling, is that what it does? It reweights the distribution of.
Something like that. I actually don't know exactly what it's doing under the hood, but yeah, it's going to be some sort of reweighting and rescaling of the distribution. I'm sure it has some functional form that it uses, but conceptually, yeah, at least maybe it's exactly what it does.
Oh.
Yeah.
When you get your, like, you find the parameter you're fitting for, you get the errors on it from how you sampled like the rest of the distribution. So isn't this gonna like overestimate errors by oversampling in the tails?
Yeah. Yeah. If you don't correct for this added bias that you've incorporated. So you're absolutely right, right? This blue curve is what you get if you drew samples, right? And you correctly point out, this looks nothing like the distribution we're trying to sample from. But we know what our bias function is, right? We defined it at the outset. So all we have to do is divide it out. Every single one of our samples, we just weight by the inverse of that bias function, right? You can see the math right here. If you just divide Q of X by psi of X, you get P of X, right? Where, again, P of X, yeah, I call that the black one, right? So the nice thing there is your bias function can be literally anything you want because you're just going to divide it out at the end. So you can just define it based on whatever is most convenient for the problem. And maybe you'll run it once and be like, oh, we need to use some function that's even more heavily skewed here. And you can try a different bias function and then divide that one out. The caveat with important sampling and adding these biases is you still need to make sure that you're drawing adequate samples from the distribution and you're covering the full range of the posterior. Right? If your bias somehow cuts off a region of the posterior, there's no way to correct for that. So as always, that comes with familiarity with the problem. You need to actually inspect the data and just say, we've got, I'm pretty sure we have enough samples to get the resolution we need, and I'm pretty sure we've covered the whole area. Any questions on this? Okay. I think I talked through everything here. Yep, I already talked through all this. Great. All right, so talking about priors a little bit, let me give you some pontification. As I've said a few times, you don't really need to get hung up on picking a single best prior, right? And one reason that I say that is you now know you have importance sampling. You can always undo the effect of your prior if you've drawn enough samples, right? So trying to say like, oh, this is the canonical prior, this is what we have to do. There's really no reason for it, right? And this comes down to this piece of advice: always state your priors. If you take nothing else away from me this week, is that whenever you publish a paper, say what your priors were. If we go back to Bayes' theorem, right, we're trying to grab posterior samples. You cannot make sense of these unless you know what the likelihood function is that you use, which most people are pretty good about saying, oh, we used a Gaussian likelihood, and knowing what your priors are. I read so many papers that people just say nothing about what their priors were. And you can kind of assume that they picked something uninformative and you can, back it out after the fact. But always, always, always state your priors so that people know what you did. And if they don't like your prior, they can fix it with importance sampling. The other point I want to make, which I think a lot of people would disagree with, is that I don't think there's such a thing as an uninformative prior. No matter what you choose, you are adding some information to the problem. A lot of times people will, kind of have this false agnosticism where they say, okay, uninformative means let's pretend we don't know anything about the problem, which, as always, if you're completely constrained by the data or you run your sampler for an infinite amount of time, that's a totally fine thing to do. But, if you set this extremely broad prior in a case where you're covering a lot of region of parameter space where you don't really think that the sampler should be, you might end up biasing your results by just spending too much time in an unphysical region of parameter space that isn't strictly ruled out by the data. So in that case, your quote unquote, non-informative, extremely broad prior is actually introducing more false information than if you had used something slightly more, traditionally informative. But, advice is the same as always. Try a bunch of different reasonable priors. You should get the same answer always, right? And then, of course, watch out there for those covariances. Make sure you've accounted for any transformation coordinates, and run tests to make sure the posterior is explored. Questions on this before we move on to how do we actually test for convergence? Okay, so there's a bunch of different things that we can do to make sure we're getting a good fit with our model, right? This is kind of the central problem of everything, is we want to make sure that we get good results, and we don't know what the answer is supposed to be. So there's no perfect way to say like, oh yeah, we've got the answer. You can't look it up in the back. So the simplest thing you can do is a posterior predictive check, which is just fancy statistics language for make sure the line goes through the data. That's all that it means. You just plot your data. You plot the posteriors on your model. In this case, I've plotted the median and then the 16th to 84th percentile. I like to use percentiles rather than mean and standard deviation because they're a little bit more robust. They also allow for asymmetry in the posterior. If your posteriors are Gaussian, then this is going to be equivalent to plotting the mean and the standard deviation. But again, probably just check both mean, standard deviation, and this percentile-based way. But again, just very, very simple. Make sure the line goes through the data. I still sometimes will be fiddling around with a problem for 20 minutes, not understanding why it's not working. And then I actually say, okay, let's just plot data. I'm like, oh, I had a typo. I was off by a factor of 10 by one parameter. The line is nowhere near the data. Of course, I'm not getting a good result. And then whenever you make these plots like this, you also want to check the residuals, make sure everything is around 0. You also, it's a good idea to normalize your residuals. So to divide by the uncertainties to get a plot that looks like this. So roughly what fraction of these points should be touching that 0 line? Yeah.
Half. Oh,
Why do you say half?
I feel like someone told me that a while back. I forget exactly.
Okay, it's not half. So, yep.
68%, 1 sigma.
Yeah, 68%, 1 sigma. Assuming that your data are Gaussian, which maybe they're not, but if the data are Gaussian, then 68% should be touching the line. Is it a good thing or a bad thing if all of the error bars are touching the line? Yeah. Yeah, it's bad. It means you're overfitting. I specifically highlight that because people are pretty good at seeing like, oh, we're underfitting the data. Overfitting is just as much of a problem. You might see it like, oh, it goes through every point. Great. No, bad, very bad. It means you either have too much model complexity or you have misestimated your uncertainties. You'll have to look at the problem to figure out what's going on, but something is wrong. Yeah.
I don't understand this plot. Can you explain it?
Yep.
What are we showing?
Yeah, I have not explained it yet, so makes sense that you don't understand it. You mean the one on the right? Yeah, you mean the one on the right, yeah? Is the one you don't understand?
I thought the question about 50% or whatever was for this plot. Never mind. Keep talking.
Well, it is. This one is just plotting, it's a histogram of this. But I had not mentioned this one yet. So if you didn't understand it, I'm saying that's not on you. Right, so specific bias is again just another fancy term for normalized residuals. Right, so if you plot a histogram of the residuals here, you want to see that roughly 68% fall between the lines plus or minus 1. Remember, we've normalized the residuals, so this should be a standard Gaussian if all of our uncertainties were estimated correctly and the data are in fact normally distributed. The blue lines are at 1, and the orange lines, that's from the data that I calculated the 16th and the 84th percentile. So we can see here, like, okay, at least within the 1 sigma credible region, things are matching up how they're supposed to look. We also want the median of the distribution to be near 0. Right? So what this plot is telling us is that everything's looking pretty good. You could, if you want, run some sort of statistical test on the distribution itself to see if it's normal. I don't know how helpful that is. Those tests are often sensitive more to your sample size than to the actual normality of the data. If you run, I think it's the Shapiro-Wilks test is the one that tests for normality. Often you get back an answer that says like, oh, to very high statistically significant, these residuals are not normal. And that high statistical significance doesn't necessarily mean strongly not normal. It just means, it can be a very small amount that because we have 10,000 data points, we can say, okay, we can be confident it's not perfectly normal. And that's fine, right? Real world data is not going to be perfectly normal. Any questions on how to use these tests to assess the quality of your fit? Looked like we had another question over there, no? Okay. Okay, and then another test that probably most of you have run at some point is to just plot the corner plots, right? And what you will hopefully see is nice smooth blobs. It doesn't have to just be Gaussians, right? Sometimes there really are covariances between the parameters. Sometimes you'll get a whole region that's filled because you're not constraining one of the parameters. That can be fine, depending on what the context of the problem is. What you don't want to see are places where it looks like the sampler has gotten stuck. So if you see in the 1D histogram, like there's like a sharp peak somewhere where it looks like the sampler may have gotten into a local minimum and not gotten out of, that's bad. One other thing I wanted to say that just escaped me. Yeah, okay. Well, yeah, you want your corner plots to look smooth and well-behaved. Questions on corner plots? Yeah.
You talked about the parameter space topology and how like sometimes if you have weird shapes and you need to do other things, you'll see that in corner plots as well. The upper corner, right? That's where you'll see that stuff.
Yeah. Yeah, in any of the 2D projections, you might see something that looks like that funnel that I showed yesterday, where you're like, you might see it narrowing and then like a few samples, and that you might suspiciously say like, oh, it looks like it's trying to get into this region, but didn't. Okay, and then the last test that we're going to want to do is to actually make sure that the chains themselves have converged. And the gold standard for doing this is the Gelman-Rubin statistic. And this is why we run more than one chain when we run our samplers, even for the ones that aren't ensemble samplers. And conceptually, all we're doing is computing the variance within a chain and then comparing it to the variance between the chains. Right? So really, we're just looking for fuzzy caterpillars, like you see on the top. Right? It's what we call well-mixed chains. It's just randomly walking around. It's reached some stable stationary state. Unlike on the bottom, where you can see the chains are clearly not matching each other, there's strong structure in them, so it's not converged. Right? Sometimes if it's not converged, it just means you need to run longer and do more burn-in. But as always, you'll need to assess the actual problem and see what's going on. So questions on Gelman-Rubin? This is an automatic output of pretty much all MCMC packages at this point, I believe. Yeah.
What value are we expecting this to generate?
Oh, great question. 1. It should be a question of about 1. There's arguments about whether you need it to be below like 1.1 or 1.05 or 1.01. But that's kind of the same argument as when people get into like, oh, do we need a p-value of 0.05 or 0.01? It's just, look at the problem, make sure it's converged. Look at, use some, not common sense, but like softer reasoning. Okay. So one challenge with the Gelman-Rubin statistic is it can fail. All of these convergence checks can fail. None of them are perfect. This is why you want to do all of these things anytime you run a model, is you're not just trying to find the failure modes you know about, you're trying to find potentially unknown unknowns. Right? So in this case, maybe we ran our sampler from this posterior distribution, obtained all of these blue samples, say our chains look well mixed, we get a Gelman-Rubin statistic of 1, our model goes through the data, but there's this whole region of parameter space that we haven't explored. And that can bias our inference of the mean and the scatter, the standard deviation of the posterior inferences. So if we suspect that this is going on, how do we check for this? Well, the only foolproof way that I know is to use umbrella sampling. Nested sampling does a reasonably good job at automatically finding these multimodal distributions. But if you really want to be absolutely 100% sure that you've explored a full region of parameter space, you've got to use umbrella sampling. This is a technique that's mostly unknown to astronomers. Biochemists have been using it since the 70s. I have really no idea why it hasn't made it into the physics and astro literature all that much, but I'm trying to change that. Umbrella sampling is another one of these things that is conceptually pretty simple and mathematically kind of tricky. Let's just say we start with some complicated posterior that has a narrow bottleneck in the middle. And if we ran just a regular sampler, we'd have a hard time moving from one of these peaks to the other peak. Right? Maybe we've run our sampler a few different times. We've gotten some different results where sometimes it clumps on one side, sometimes it clumps on the other. And we say, okay, we need to figure out how to get this to work smoothly altogether. So what we do is we split it up into 3 different regions. In the jargon, these are sometimes called umbrellas or windows, but it's just, we're adding these bias functions, and these are the same as the bias functions that we talked about with importance sampling. Importance sampling can be thought of as the single umbrella case of umbrella sampling. So you put these bias functions, in this case I've used triangular biases just because they're simple to calculate, and you've run your sampler 3 times. Right? So umbrella sampling is brute force. It's slow. It's going to be at least 3 times slower in this case because you have to run your sampler 3 times. But you'll also notice that these umbrellas overlap. And this is the key to making this work, is we draw samples under the blue umbrella, the orange umbrella, and the green umbrella, and then we're going to compare how many samples from the blue umbrella fall under the orange umbrella and vice versa, and how many samples from the green umbrella fall under the orange umbrella and vice versa. And that's going to allow us to glue these 3 independent runs together after the fact. So we draw the samples separately, and now we have these 3 distributions. These still include the effect of the bias function, right? You can see that bias serves to like raise up the middle of this orange one here and kind of like widen the mountain pass that you have to go through. So if we just added these together, we'd not get the right results. But we at least now have drawn samples over the full range. Any questions so far? Okay. So this is where the mathematical trickiness comes from, is we need to basically calculate the integral under each of these regions. And the problem is that we have our samples that we've obtained under the umbrellas entering in on both sides of the equation. If these equations seem confusing and don't quite make sense right now, that's fine. One of the practice problems today is going to be working through this tutorial I've written, which steps you carefully through how to do all of the math. But essentially what we're doing, and there's a few different ways that you can try to calculate those integrals. The way that I've used is this matrix-based way, where you are, calculated matrix, which basically says, how many samples from one umbrella fall under the other umbrella. The easiest numbers to understand are the two corners. Here we can see, none of the blue samples fall under the green umbrella and vice versa. And then, the relative numbers here with higher numbers, meaning more overlap. Again, you'll work through the tutorial for the practice problems, and it'll all make a lot more sense when you're actually like going through it. Okay, questions on any of this? Yeah.
The previous slide.
Mm-hmm.
Hard time understanding the form of bias spread. Is it always part of the? Is it always supposed to be like that? Like, why are we not taking the simpler overlapping three box?
Yeah, you could. You could absolutely use a simpler overlapping three box. The reason that I use these in this specific case is I wanted to upweight this region in the middle. If you used, so for the blue and the green umbrella, just a box function would have worked fine. You would have been able to sample from those. But if you put a box here, you would still have a high probability region here and here, separated by a low probability in the region in the middle. So you would still have trouble navigating through. Well, it's a probability distribution, so it's going to be normalized. So even if you drew it bigger, you'd then divide it down by the height, and it's got to have an area of 1 under the curve. Yeah. If you want to just use boxes, you could use many, many more narrower umbrellas and just like step through these little slices and then glue all those together. Yeah, but that would take longer. In this case, a bias that upweights the low probability region is probably the way to go. It's easier to draw your umbrellas when you know something about what you expect the posterior topology to look like. There are prescriptions for how you can just automatically generate umbrellas if you don't know what the posterior topology looks like. So you don't have to have that prior knowledge, but the more you have, the easier it's going to be, the faster your sampler is going to run. Okay. And so, right, the question really is, how do we identify unknown unknowns? As I've stressed the past 3 days, there's no substitute for domain expertise, right? You know the astrophysics you're doing better than anyone else in the world, so put that to work for you and say, like, okay, this makes sense or this doesn't make sense. The more physics you can impose on the problem, usually the less you're going to have to do things from an only data-driven approach. Do exploratory runs. Don't worry about getting things right on the first try. You almost certainly won't. But do quick and dirty runs, start to get a lay of the land. And then if you absolutely positively have to make sure that you're exploring some region of parameter space, use umbrella sampling. Actually, I've very rarely ended up using it for actually fitting a final model for data, but I've used it, for example, to convince myself that other sampling techniques are doing what they're supposed to be doing, right? Like, if I'm fitting a bunch of exoplanet transit light curves, I've compared umbrella sampling and nested sampling on, a few dozen of them, say like, okay, nested sampling is behaving. I see where the failure modes are. Now I'm just going to run nested sampling on the other couple thousand in my sample. And as I said, don't only rely on your sampler, right? The more work you're making your sampler do, the slower it's going to be. So do as much work as you can at the top to clean things up. So we started a few minutes late, so I'm just going to go just a couple more minutes just to give you a real world example of how I've applied this in my own research. So the big problem that I've been working on for the last few years is trying to measure the eccentricities of exoplanet orbits. And just to give you a little bit of physics background so you understand what's going on, right? When a planet transits in front of its host star, you see the light dim. The fraction that it dims, we call the transit depth. The time of the transit, we call the transit duration. And then the inferred distance from the center of the star, we call the impact parameter. And to infer the eccentricity, we need to know both the path length it takes, which is related to the impact parameter. That's just geometry. And we also need to know the velocity of the planet during orbit. right? An eccentric orbit moves faster or slower during its orbit compared to a circular orbit, depending on the orientation relative to our line of sight. And we compare our observed transit duration to what we predicted if we were on a circular orbit. So there's a few challenges here. The biggest one is that this is an under-constrained problem. We only have one observable, the transit duration, and we have 3 unknowns because real transit light curves are noisy, and so we can't measure the impact parameter directly, at least not to any sort of precision in almost any case. It's an under-constrained problem, which tells us we need to use a population-level hierarchical approach. Right? We can't infer necessarily the eccentricity for an individual object, but we can for a population of objects by pooling the information. The other challenge ends up being measuring this impact parameter. Right? Kepler was optimized to measure transit depth and period very, very well. It did those great. Transit duration we can usually get very well, but there's almost no information in most light curves about impact parameter. And because that's covariant with eccentricity, we need to measure that really well. Unfortunately, it turns out that's a really, really tricky quantity to measure. And it's not something most people concern themselves with because in a sense, it's a nuisance parameter a lot of the time. It's just relative to our line of sight. It's not even something that's fundamental about the planet. And the sampler can misbehave when you go from an ordinary non-grazing to a grazing geometry because the shape of the light curve changes sharply, which leads to this strong covariance in the posterior. I should say that the reason there's this covariance is because real stars aren't uniform brightness. There's limb darkening because of your viewing angle. They look darker at the edges. So here, this is why I developed umbrella sampling, is I noticed a lot of the time the sampler was getting stuck near this grazing impact parameter, and we had to make sure we were exploring the full posterior topology. We also, as we were exploring the problem, found that because there was a coordinate transformation that wasn't accounted for, there was this implicit prior on impact parameter that resulted from using what seemed like an entirely reasonable prior on stellar density. It just, it went unknown for like 8 years. So it was a really, really subtle thing and only popped up after Gaia launched and we got better measurements of stellar density and realized this was there in the first place. And then this was comparing to make sure that we got the same answer from nested sampling and umbrella sampling, which we did. So, just walking through, this is where, I applied all of these techniques in practice. So kind of the whole suite of things was needed in order to get the problem of measuring impact parameters to get eccentricities. So my point there was not just to pontificate about my research, but to point out, right, there wasn't just one tool that we used. We needed a lot of different things to solve these different problems, right? We used hierarchical modeling, umbrella sampling, nested sampling. We used importance sampling in order to convert a 7-parameter problem into a 5-parameter problem through some nice mathematical tricks, which made everything much, much faster. And so you should do the same thing in your own work, right? Use whatever tools are necessary for the job. Don't get fixated on just finding one. As always, I'll leave you with some more resources that are good to use. This is the same textbook I've been suggesting you guys all read throughout the week. I think you all have the PDF at this point, so use it. It's great. And these are, to my knowledge, the only 2 examples of pedagogical explanations of umbrella sampling in the astro literature. So hopefully you'll find them helpful. As I was learning the technique, I found one of the biggest hurdles was just it's really hard to read biochemistry journals because they have different names for everything. So hopefully you'll find those helpful. All right, and I'll take any last questions, and then we'll leave it there.
There's a question from Zoom regarding the umbrella sampling. How is the final unbiased probability distribution reconstructed from the biased simulations? Using weighted histogram analysis method, maybe? Question mark.
So the question was, how do we recombine the umbrella samples into one? Yeah, so the weighted histogram analysis method, or WHAM, is one way of combining those samples. That's not the one I used. I use this technique called eigenvector method of umbrella sampling. I know it's called emus. They're equivalent. They do the same thing. So yes, WHAM is a very popular method that you can use. It's been a few years. I don't actually remember how the math works out, but that's definitely one option. Any other questions? Okay, why don't we take a quick break then, and then we will come back and do the problems.
How long's the break?
Brian?
Let's do 15 minutes. Great.
Great.
So we're